All right, let's dive into something straight out of science fiction, the railgun. This is a fascinating piece of tech that uses the fundamental forces of the universe to launch things at just unbelievable speeds. So how does it take raw electricity and turn it into pure kinetic power? Let's break it down.
First things first, you have to forget everything you know about traditional cannons. There's no gunpowder here, no chemical propellants, no fiery explosions, nothing like that. Railguns run on a totally different principle. We're talking about raw, controllable electromagnetic force.
And that really gets us to the core question, doesn't it? How can simple electricity, the same stuff that's powering your screen right now, be harnessed to create a force that can launch a solid object at hypersonic speeds? We're talking Mach 6. Well, that's exactly what we're about to figure out.
Okay, let's start with the absolute basics. At its heart, a railgun is really just a massive energy conversion machine. Its entire job is to take electrical energy and transform it, as efficiently as possible, directly into kinetic energy, which is just the energy of motion.
So the official name for it is an electromagnetic projectile launcher. It's a pretty simple description, but it really captures the magic of what's happening, using the invisible forces of electricity and magnetism to create a massive physical push.
So how does this invisible force actually work? The entire principle, the secret sauce behind a railgun, hinges on one key concept from physics. If you get this one thing, you get how the whole system works.
And here it is, the Lorentz force. Now that might sound intimidating, but the idea is surprisingly simple. All it means is that when you run an electric current through a magnetic field, you create a physical push. That's it. A railgun is basically a machine designed to take that one fundamental rule of physics and amplify it to an absolutely incredible degree.
You can almost think of it like a recipe for force. You need three key ingredients. You need a powerful electric current, that's your I. You need a conductor for that current to flow through, which has a certain length, L. And you need a strong magnetic field, B. When you mix all three of those together, the result is a powerful forward push. The more current, the stronger the field, the stronger that push becomes. So how does the railgun actually use that recipe? Well, it happens in a few quick steps. First, a gigantic electric current flows down one rail, it crosses through a conductive piece called the armature, which holds the projectile, and then flows back up the second rail. That completes the circuit. And that massive current, just by flowing, generates an incredibly intense magnetic field between those two rails. And there you have it. The current in the armature is now sitting inside that magnetic field. The two interact, creating the Lorentz force. And that force is what launches the projectile forward at an absolutely immense speed.
Okay, so we've got the physics down. Now let's look at the actual hardware. What are the essential pieces and parts that make a railgun actually work?
You can break it down into four main components. You've got the rails, which do two jobs. They conduct that massive current and they generate the magnetic field. Then you have the armature. That's the moving part that closes the circuit and actually pushes the projectile. Of course, none of this works without a huge power supply, which provides these insane bursts of energy. And where does it get that energy? From capacitor banks. Just think of them as giant, super-fast batteries that can dump all of their stored power in an instant. But here's the catch. When you try to channel this much raw energy, you run into some of the most extreme engineering challenges on the planet. I mean, the forces involved are just almost beyond comprehension. They push materials and design to their absolute breaking point.
Just how much energy are we really talking about here? Well, a single shot requires tens of megajoules. To put that into perspective, 1 megajoule is the same kinetic energy as a 1-ton car traveling at about 100 miles per hour. A railgun unleashes dozens of times that amount of energy in just a fraction of a second.
And what do you get when you release all that energy? You get speed that's just hard to wrap your head around. We're talking about Mach 6. That's 6 times the speed of sound. A projectile moving that fast doesn't even need an explosive warhead. Its own kinetic energy is what delivers the devastating impact.
So, how does that compare to what we have now? Well, the difference is pretty staggering. Conventional artillery, some of the fastest stuff we have, tops out at around 1.7 kilometers per second. A railgun can nearly double that, reaching up to 3 kilometers per second. It's a truly revolutionary leap in sheer velocity.
But all of this incredible power comes at a huge cost. The engineering problems are immense. The sheer force and heat can literally melt and tear away parts of the rails with every single shot. Just storing and then delivering that much power safely is a monumental task. The current is so intense it can even turn the air in front of the projectile into plasma, which actually creates drag and makes the whole system less efficient.
So, Even with all these massive challenges, the potential is so great that research is still moving forward at a rapid pace. So why does all this matter? Let's take a look at where this kind of technology could actually take us.
Well, the most obvious application people talk about is for naval warships, giving them incredible range and power. You could also use them for missile defense, firing projectiles fast enough to intercept incoming threats. But beyond the battlefield, the potential might be even bigger. Imagine a massive, ground-based railgun that could help launch payloads into orbit, which could dramatically reduce our need for traditional rockets.
And you know, this quote really says it all perfectly. Railguns are where theoretical physics, the science of these invisible forces, smashes right into the brutal, harsh reality of practical engineering. It's a field that is constantly pushing the absolute boundaries of what we know and what we're capable of building. And that really leaves us with one final, powerful question to think about. We are literally learning how to harness the fundamental forces that hold the entire universe together. As we get better and better at mastering this technology, how is it going to redefine our world? Everything from the way conflicts are fought to the future of how we explore the stars.